I wish I could make it fade, but I just have to cut it. Boom. Okay. Good morning, everyone. We are going to start our webinar very soon. Before we do that, I'm going to make one request. If you're a chemistry student, which most of you are, so you can see on screen the plan for the week. We are here Tuesday. So this is, I'm going to call him Dr. Finnerty. He's not really a doctor yet, but he's going to get used to it. So this is Dr. Finnerty. He's pursuing a PhD in environmental engineering. So trying to save the world one technology at a time, huh? Really? Yeah. Okay, great. So the request I am making, tomorrow the tournament starts for the Crown Jewels IC 2020. And last time I looked, which was 20 minutes ago, we have 23 teams. So I'll scroll up for those of you who need to see it. See this team number? And you can have up to 3 people on your team. We have 23, which is really bad for a tournament. So I'm asking you to consider, please be team 24. Please be team 24. And then that's much better for the tournament. So we'll be setting up the tournament bracket. Mr. Myers is taking charge of that. This afternoon is when we'll try to do that. So please do sign up before we make the bracket. Otherwise, it's a big mess. All right, there's some people who might be on this page right now. So please, 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 please. So let me go back here. You can get to that page, tinyurl.com/Crown Jewels Tournament, Crown Jewels Tournament. You can also get there by just clicking on the link if you have the online document, which is in your Google Drive. That's my phone. I'm going to make it stop. Boom. There we go. Okay, so you can get there by the link, or you can get there by typing, and that's the way you do it. Okay, boom. All right, I'll look at the end of today and see that into today's webinar and see if we got a team 24. If so, I'm happy. If so, I'm happy. All right, so I think that's all I need to say, which means I'm going to turn it over to Dr. Finnerty, and he'll be sharing his screen. So I'll stop sharing mine.
Let's see. All right. Are you guys seeing a presentation?
I see a picture of your desktop.
Okay, let me try that again.
I got Ms. Honeycutt here. All right.
All right. How's this? Is this looking any better?
That's the presentation. Yes.
Sure. All right. Cool. Well, yeah, thank you, Mr. Sogo, Mrs. Perkins. It's great to see both of your guys' faces. I had you guys when I was in high school, which is a long time ago now. I also have Mrs. Hartford, who I think some of your guys' teachers. I'm going to talk to you guys today about what I've been doing in my graduate work, and that's been working on developing a sustainable desalination technology. And I'll kind of dissect that in this presentation. But before I dive in, I wanted to kind of like catch you guys up on what I've been doing since I graduated from high school. So back in high school, I was really interested in sustainability. I was a part of the Surfrider Foundation Club, collecting those water samples. Lived near Crescent Bay, so that was my go-to beach, catching the runoff there. I also, with Mrs. Hartford, we worked on developing a recycling program on campus, and so that was always kind of like a big thing for me. Moving into college, I really wanted to start doing research in that field. And kind of the first opportunity I got was actually working with the Berkeley Center for Green Chemistry. And so that's kind of the picture that you see on the left. I was working with a number of students with this center, and they were trying to develop kind of these instructional labs, kind of like the ones that Mr. Sogo has designed for you guys, that emphasize these principles of green chemistry. And so we were seeing like if they worked, if they didn't work, and like, you know, modifying the instructions to make sure that like they're clear. And that was kind of my first it wasn't necessarily like a research position, but it kind of was like my first, step into that world. For my undergraduate research.
Casey?
Sorry?
For those who are not familiar what green chemistry means, you should probably just tell them what that.
Yes, yeah. So there's the movie Dark Waters, I think it was the name of it. And so that came out recently. If you have nonstick pans at home, there's basically this chemical that coats those pans that has these wonderful properties from kind of a user standpoint. But from an environmentalist standpoint, those chemicals, they'll kind of gradually break off of your pan and kind of go into your system and be like many of those same properties that make them resistant to heat and degradation and all these other things make them really hard to break down in the environment. And so kind of one aspect of green chemistry is like really thinking about this molecule kind of from its creation all the way to its ultimate destruction so that it doesn't create kind of these problems in the environment. Does that, yeah, there's more, but yeah, it's a cool field. For my undergraduate research, so I was studying chemical engineering, and there's a big focus in our program on biofuels and biofuel synthesis. And what I was working on was I was actually working with a engineering salmonella so that it could kind of be like a miniature factory that produced cellulose and would also secrete that cellulose. And cellulase, and it would secrete it. And so I was trying to engineer the pump, this like natural pump that it has to secrete these proteins from within the cell outside of the cell so that they can make more. But it was around this time that I felt that like the research that I was doing was a little too far away from the impact that I was wanting to have. And it was around this time that I was introduced to my first environmental engineering course. And in this course, we studied these natural treatment systems. You can think of them as like wetlands or ponds. And basically you can design these ponds and wetlands to actually treat raw sewage. And so here's us kind of wading around in one of the wetlands. I had waders on, so it was roughly sanitary. And we're measuring the pH and the temperature and how that affects kind of the treatment efficiency of this system. And that really kind of sparked in me this interest in water. Water is just so prevalent in kind of every aspect of life that research kind of on water quality improvement seemed like a nice nexus of like where I could be working and it could be having this direct impact. And so I got a chance to kind of explore this interest more during internship during my undergrad. And that was working in Nicaragua on kind of evaluating the use of this water filter that was kind of deployed in 3 different communities. And then also designing and constructing a latrine. And you can kind of see our team there with this new latrine that we had just built. After undergrad, I went on to work for a membrane manufacturing company. They basically make these industrial water filters. And I was really curious as to how, like what technologies were out there, and particularly pertaining to desalination. And what I was interested to find was that there actually aren't that many ways of desalinating water. If you're in an industry, you're pretty much going to be using reverse osmosis, and I'll explain more on that. And as my job was being a technical service engineer, I was usually called up whenever there was a problem with this particular technology. And so I got really intimately aware of the capabilities of reverse osmosis, but also its limitations. And it was those limitations that really kind of drove me to want to go back to graduate school and try to develop a sustainable alternative. And so, what's so wrong about reverse osmosis that I wanted to dedicate, 5+ years trying to come up with this alternative? Well, so before I get into that, I wanted to quickly go over what reverse osmosis is. And so for those of you who are in AP Bio, you might be familiar with this topic. Mrs. Harper was telling us that you guys did this carrot lab where you put carrots into different solutions with different salinities. And for the carrot that went into the kind of the pure water solution, the hypotonic solution, you can kind of see this osmosis in play where you have the water from the pure water going into the carrot. And the reason it does this is osmosis is kind of this tendency of water to want to dilute concentrated solutions. And so this carrot has, these cells, and in those cells they have these sugars and salts, and the water wants to dilute that, and so it actually will diffuse or osmose through the membranes of those cells in order to do that. And so reverse osmosis is just the opposite of this. You can imagine like taking that carrot and squeezing it, and if you're strong enough to squeeze it to push that water from within the cell through those membranes and back out of it, that's basically what reverse osmosis is. And that's kind of the industrial process. You start with a saline water source. You can think of seawater. You use a really high pressure pump to send it to this reverse osmosis membrane. And then in that membrane, they have basically curled up in there is all this flat sheet, which you can think of as like a filter. And under this really high pressure, water is able to permeate through that membrane while salts are rejected. And the water that permeates through is this, drinking water that you see here. Some of the challenges with this process is that this is super energy intensive. Energy needs to be supplied to that pump, and based on how saline that initial water source is, you have to supply even more energy. And there's kind of a rule of thumb with water treatment in that the smaller something is, the harder it is to get out of your water. So you need to input more energy in that process to remove it. When we think about dissolved salts, that's pretty much the smallest thing that can, show up in your water. And so it's very, very energy intensive process to remove it. Another aspect of reverse osmosis that, could be improved is that you can't just treat this, raw seawater. If you were to send that straight to your membrane, all the algae, all the particulates, the sand, that would clog up your filter, and it would, cause you to need to replace it fairly frequently, which is really expensive. And so you need all these pre-treatment steps and the surrounding infrastructure in order to allow for this reverse osmosis membrane to do what it's supposed to do properly. And then finally, the last challenge with reverse osmosis is it'd be nice if you just have this one inlet and one outlet, but that's actually not the case. All those salts that are rejected by your reverse osmosis membrane are actually concentrated into this brine stream. And this is actually a pretty consequential amount of brine, especially for seawater desalination applications. You're pretty much producing just as much brine as you are pure water. And so you need to do something with that brine. And unless you have kind of an ocean nearby, which is the case for seawater desalination, you have to do alternatives. So if you are, working on desalinating groundwater or industrial brine, you have to rely on either really land-intensive processes like using evaporation ponds, or even more energy-intensive processes like brine crystallization. And so what I've been doing is actually not necessarily new. It's maybe the most ancient way we've been desalinating water, back to kind of mariners who were, sailing across the sea, needing a water source. They would take water and they would heat it up in the sun and allow it to evaporate. And what I'm going to show for you here is just kind of like dissecting this process a little bit more. And so what you can see here is, on the left, we have a beaker of water, and then on the right, you kind of are zoomed into that air-water interface. And we have kind of at this, upper part, we have these little circles that we'll say are just liquid water molecules. And these water molecules, they're not static. They're moving around. It's a fluid, so they're bumping into one another. And every so often, these collisions line up so that water molecules have enough energy to actually leave the liquid phase and enter into the vapor phase. And we know this as evaporation. You can actually speed up this process, and this is kind of what those mariners were doing when they put their water in the sunlight, is they increase the temperature of their solution. And by doing this, you actually are increasing the energy of these molecules, and you're increasing the likelihood that you'll have these collisions that result in this phase change. And so, as an engineer, we're always thinking, okay, how can we improve this process or make it more efficient? And what we have been working on has been developing these materials that you actually put at the air-water interface. And so they're light absorbing, so they're dark in color, they're porous, so that they can use capillary action to kind of draw water into their internal structure. And when you expose them to sunlight, this material will heat up, And when it heats up, it'll kind of discharge that heat to kind of this thin film of water in its pores, and it'll accelerate this evaporation process. And then this can repeat using capillary action to replenish the water. And this is a process that we call interfacial solar vapor generation. And it's basically just a fancy way of saying we're trying to increase the rate of water using these photothermal materials. So with that, I have this little guide to kind of remind me to take pauses every so often to see if there are questions. So yeah, I want to take a quick break to see if there are any questions out there.
So you who are in the audience, you can ask your question via the chat box, and the teachers here will be monitoring the chat. So we'll look and try to pick out some good questions from there. If you do want to ask your question out loud, if you can raise your hand, which is a feature in Zoom, then we can look and we can take your question out loud. So I'll be looking at the chat. The other teachers will be looking at the chat. And I will encourage you other teachers, if you have questions, feel free to ask your question out loud rather than going through the chat. So my first question to you, Casey, if I go buy, the purified water at the grocery store, is that done with distillation or reverse osmosis? Or
one of the last projects actually I worked on when I was working with Tricep was a reverse osmosis plant in Ontario, California, which does a lot of the water bottling for Southern California. So if you've gotten like the Kirkland brand water, that if you look on the back, it'll say like bottled in Ontario. And so they start with groundwater, and they use this reverse osmosis system to purify the water. And then all these different companies basically have their own salt solutions. So they'll add salt back into it for taste. And so all the different waters actually have like a slight taste that's their own like special chemistry. But that's basically how it works. They take everything out and then they put what they want back in.
Really? Okay. All right. So we should read the labels on the bottles. So
yeah.
Next time you're in a store, students, which may be sometime from now, but next time you're in a store, look at the water that you buy and see if it tells you where it's processed and is it processed by reverse osmosis and what did they add back. All right, we're getting some questions in the chat. The first question is from Luca Elganian, an ACR student. He's asking, can water vapor have salts dissolved in it?
That's a really good question. And I think, so technically, yes. So if you do these tests, like all these papers will report kind of their like initial feed water solution, and then they're like the condensate water solution. There will always be a little bit of salt in the permeate, and it's like kind of ambiguous as to like how it actually gets over there. And one answer is there could be contamination in that permeate, but the more likely, or that's probably the most likely source of it. But what we're finding with these materials is that evaporation isn't this like clean process where water will just like a single water molecule will just evaporate one at a time. Every so often you can actually get these clusters of water. And when you have a cluster of water, that can surround kind of these salt ions and still be airborne. And when it does that, it can actually carry that salt from the your like initial feed solution over to your condensate. And that's kind of one way that it can carry over. This process happens, very, very minimally compared to kind of most of the water evaporating. And so even though you are still getting some carryover in this gaseous phase, you're still getting a lot of rejection of that, or a lot of the salts are still being retained in that original feed water solution.
Yeah, and I think you have some video that will show that very clearly. Next question is from Taro. Taro Sakai is Dr. Finnerty's cousin.
Yes, yeah.
His question is, do brine shrimp come from the same term you said before, which was brine management?
Yeah, no, brine is kind of this catch-all term for like salty. And so, yeah, the brine shrimp, I'm guessing, are like processed in some way that they're exposed to either like directly into like salt or a very salty solution, or they live in kind of these like really high salinity ranges. I'm not familiar with brine shrimp in particular, but yeah, that when you hear that word brine, think lots of salt.
And last question we'll take at this time is from Charlie Dickerson. And he's saying, since the reverse osmosis produces brine, if that goes back in the ocean, are there major ecological repercussions?
Yes, yeah. So I think there's been a lot of talk in Southern California about these new desal plants, and we'll kind of see how far along they get. But in order for, why reverse osmosis in general is really hard to implement is it's not necessarily, like, part of it is the operating costs, so all the energy we were talking about with reverse osmosis, but a lot of the initial upfront costs has to do with, like, building out that infrastructure on how to discharge your brine. And so if you were to just dump your brine into the ocean, it's actually, because it has so much salt, it's actually denser than seawater, so it could sink to the bottom and create this really, like, hypersaline zone, which would be, if fish were to swim there, their bodily functions wouldn't work properly, and so they have to design these kind of diffusers. So they basically, as they are discharging, they kind of like take in seawater to dilute it, and then by the time they discharge it, it's comparable enough in terms of density to seawater that it doesn't sink to the bottom. And that's, like, really expensive infrastructure to build out. So yeah, that's a big concern of a lot of these seawater desal plants.
Okay, I will ask you to clarify. So the ocean water is 3 to 4% salt,
Mm-hmm.
and what's the concentration of salt in the brine that's being emitted?
Yeah, it's usually about double, so about 7%. Yeah.
All right, thank you. Okay, so we'll let Dr. Finnerty go on with some more slides, but there will be another opportunity for you to ask questions in a few minutes.
All right. So we've been talking about this, developing kind of this porous, light-absorbing material that floats at the air-water interface. And so now it's kind of our task to try and build a material that kind of mimics these properties. And so my lab has kind of in the past focused a lot on graphene oxide. And graphene oxide is kind of, you can think of graphene as just this, like, this fencing, or like this, like, flat sheet of just, like, carbon bonds all the way through. Graphene oxide is kind of the slightly messier version of that, where you have these oxygenated functional groups. So you have your carboxylic acid, you have your epoxy groups, your hydroxy groups, kind of interspersed in this graphene oxide molecule. And you can see here, this is graphene oxide in its powdered form, so it's very dark. And one benefit of having these oxygenated groups is that they allow for this kind of interactions with water. So it makes these graphene oxide much more hydrophilic than, say, graphene by itself. And so with these, what we decided to do is we used graphene oxide, and we wanted to kind of introduce it to a filter paper substrate. And then that got us kind of this dark, light-absorbing material that we were wanting. Now, it's good that this material is hydrophilic, but it's almost too hydrophilic in that if we were to expose this directly to water, these graphene oxide molecules would actually redissolve into that water and leach out. And that's not ideal for kind of building this material. So we introduced these two cross-linking agents. The full names are really long, but the acronyms are TETA and BDGE. You can kind of think of these as chain links that will anchor these graphene oxide molecules to one another and fix them in place. And you'll notice that just kind of for you chemistry fanatics out there, this amine group will actually react with this epoxy and kind of create this chain coming out. And then you'll notice that this BDGE has another epoxy that'll react with this side, and they'll kind of link from there. And that's how that reaction works. And so by introducing these to chain them all together, we're able to get a more chemically stable material. And then how we process all these chemicals, we actually used a flash freezing process. So we took our filter paper, we introduced this solution, so it's still wet, and then we brought that into liquid nitrogen. And what liquid nitrogen does is it's extremely cold, and it'll freeze our mixture really quickly. And when that happens, basically water is going to is going to freeze, and it creates these kind of small crystals. And when it forms these small crystals, it actually pushes these chemicals out and into this kind of structure that you see here. And then we put the material still frozen into a freeze dryer, which is a chamber that lowers the pressure so that these water crystals will actually evaporate and they'll sublime, and that's how we remove the water from the system. And so what's left is kind of this porous structure that you see here. And you can kind of see these fibers, and that's actually the filter paper fibers that you see there. And kind of this webbing that you see is the graphene oxide cross-linked with these cross-linking agents. And so we felt that these kind of properties combined would be a suitable interfacial solar vapor generating material. And so how we tested these materials is we brought it into a lab. We had a beaker of water, as you can see in this image here. And then we floated our material at that air-water interface, and then we put it on a mass balance. And we have this special lamp that produces kind of the same spectrum and light intensity as sunlight. And we expose our material to that sunlight, that simulated sunlight, and measure the mass loss over time. And so that you can see kind of the inverse of that being the mass evaporated. And when we look at this, our control was just kind of a beaker of water, no material added to it. We got this kind of baseline rate, and when we introduced our geo leaf, is what we've been calling it, we saw an increase of about 59%. And before I kind of move forward here, I wanted to clarify a unit of measure that I will probably be using a lot throughout this presentation, and that's LMH. And so that's liters of water per meter squared per hour. And this is what's known as kind of a flux rate. So it's like, you can think of it as a flow rate normalized by a unit area. And so for our particular case, we're evaporating water, and we want to know the rate at which we're evaporating water. So that's the flow rate coming out. And so that, we're not skewed by how big or how small our area is, we divide it by the area by which it's evaporating. And so that's LMH. So if you hear me say that, or if you need me to clarify, definitely let me know. But so we were able to get this increase, which is good, but we felt like something was holding this process back. And so what we did is we took a thermal camera, and we looked at kind of the equilibrium temperature profile of our control and our geo leaf when it's floating at the air-water interface. And with the leaf, you can see that it is doing its job. It's absorbing that light, it's turning into heat, but then a lot of that heat's getting conducted away into just heating up the water, as opposed to channeling it towards evaporation, which is what we want. And so we developed this, and you can see the heat sink there. We developed this tree-like configuration so that you can see this material here. You can think of that as a paper towel. It's like a material that wicks water up kind of against gravity and will supply our geoleaf with water without the geoleaf actually being in direct contact with our water. And when we look at the thermal image of this, we can see that we're getting much better retention of heat at our evaporation interface, which is what we want. And so looking at this performance, we tested it the same way, and you can see that we're now getting a much more significant increase of 185%, which is wonderful. But we'll kind of qualify that in a couple of slides. One other thing that I wanted to show you guys is the previous tests have been done with just pure water. But what we're really interested in is what happens when you do this with like a saline water source, like seawater, or in this case, really concentrated seawater. This is about 4.5 times the concentration of seawater represented with sodium chloride. And we're gonna try and show this video. It may get a little glitchy around day 3, but basically what I want you to focus your attention on is what happens to the salts right at this evaporation interface. I'll give it a second. All right. So you can see the water level going down, and as it goes down, we're getting more and more salts depositing on our surface. At least I'm hoping that's what you saw. And what's interesting is that even though this took place over the course of 5 days, and you can see the data here, despite that extensive accumulation of salts on the surface of our material, we didn't see a performance decline in the flux. So this, the slope here stayed relatively constant throughout the whole test, which is great. Even though we're getting this accumulation of salt, it's not necessarily inhibiting the performance at this stage.
Go ahead and play that video again, Tacey.
Sure.
So we're
And
looking
this
at
is also,
evaporation of water in the beaker,
yeah,
and then salt appears on the top because it doesn't evaporate.
correct.
But the water is being carried up to the top by the
There's a,
Pascal equivalent.
yes,
Okay.
right.
So it just climbs up, which is really cool. Yeah, excellent.
And so, yeah, and this is actually another breakpoint for questions.
Yeah, great. This is a good break point. So once again, teachers will be looking at the chat. Please type your question into the chat, and we'll get to it as soon as we can. Okay, here's our first question, which is an interesting, thoughtful question. It's from Amar Bhatia. Is there a potential for the, let's see if I can translate it, interfacial solar vapor generation, ISVG, to be used as a power source as well as a water purifier, possibly through the movement of evaporated gas particles or the gravitational potential energy of resulting purified water? Whoa.
That is an incredibly insightful question. So there have been studies of people trying to do that. One thing that I've tried to get better at while being a graduate student is really understanding not only how mass moves around, but what happens with energy. And so there's a lot of energy in kind of this waste heat that just kind of goes into the environment. So to your point, yes, you could pretty much how a lot of energy generation happens today is you vaporize water and turn it into steam, and that basically spins this turbine. And that spinning, from physics, you'll recall, you'll have magnets on it, and when you move magnets in a field, I think it generates an electricity. And I'm definitely oversimplifying that, but that's one way you could do it. There is another way. So when you condense the water, it actually releases all the energy that went into vaporizing it. It kind of retains in this gaseous state, and then when it condenses, it releases that energy. And there are these things called thermoelectrics, and they basically, if they're a material that if on one side it's warmer or colder than the other side, it actually is able to generate an electric current as well. And so if you have kind of a condensing surface that uses one of these thermoelectrics, you could actually use it to generate some power. I'm trying to think of, there are a number of ways. And so I really like your thinking and creativity in that question. So yeah, there are other I've mentioned here.
The thermoelectric was something I wanted to do. If we weren't on quarantine, we might be doing that in the classroom, because I got the little demonstration one, and I think it's a really cool idea. You just put heat on one side and cold on the other, and it makes electricity.
Yeah.
So you're saying you could build that into a system here that the energy comes from the sun, but instead of wasting some of it, you can get some electricity out of that process, which is excellent. I have a question. Do you know the water that's left in the beaker? Is that even more saline than it started?
It is slightly, but not significantly. So a lot of the salt will just kind of precipitate on the surface of our material. But because you have this really high concentration layer up here, the salt's going to not want to kind of be wicked up with the water as much. It's going to feel that concentration gradient, and so it's going to basically slow down the rate at which it enters the salt kind of layer. And for that reason, you do get a small accumulation of salt, but it's not super significant from what we've seen. And it can be kind of tailored based on how you supply the water.
Okay, here's a question from Ms. Honeycutt. What do you do with the salt?
That's a good question. So I haven't worked too much on that side. So a lot of times, and this is kind of what I would want to avoid, a lot of these brine generating processes, if they send it out to an evaporation pond, a lot of, like with seawater and some other sources, it tends to be this mess of salts, and it usually will end up in a landfill. If you can take this salt and do some kind of purifying process, so if you were to like extract just purely sodium chloride, or if you were to calcium carbonate, or like these specific species, if you're able to isolate those, that's when these things start to have a lot of value, and you can actually sell them to various applications. So that's kind of not been the primary focus of my research, but yeah, understanding, what is the value of this, previously considered waste stream has been something that I've been trying to, tease out.
Yeah, that's excellent. So you don't only get the water, you get other useful things, which may be some energy or maybe the salts itself. Okay, great. Let's let you continue now.
All right.
So we'll have another pause point in a few minutes.
Yes. All right. So it's good as a researcher, no matter what field you're in, it's good to kind of like take a step back from the lab and take a step back from the lab and kind of like understand like how does this compare to like other technologies. And so in this particular case, what we wanted to do was compare to reverse osmosis, say like an under the sink operation. And this image that you have on the left is actually a project that we're working on. It's an island in Indonesia that's really high population density. And as you can see here, there's all these houses that are built up, and it's actually the original landmass is much smaller than where the city sprawl has kind of extended out to. They've actually kind of built on kind of the surrounding coral reef. And so in places like this where you don't have a lot of space, it's really important to also consider kind of the spatial constraints that you're working on. And so for this comparison, we thought size would probably be one of the best metrics. And so for an under the sink reverse osmosis system, you're able to produce about 75 gallons per day if you're just fully running it. And the size of it is about 0.15 meters squared. And for our material, if we were to match that production rate, we would need a size of about 5.9 meters squared, which is not great for us. And so this has really focused us on trying to increase the rate at which we're able to vaporize water so that we can kind of spatially match these other technologies like reverse osmosis. And so how we aim to achieve this was one, by increasing the area for evaporation. So you can kind of see this was the previous setup that we were working with before, and we basically ran the same sort of synthesis procedure, but we used a cotton humidifying stick. And so this gave us kind of this three-dimensional material that we're working with here. And to compare these two, we made up this term called Evaporation Area Index, or EAI. And this is basically the ratio of the total surface area that you have for evaporation relative to your projected ground area. And so you can imagine for a flat two-dimensional material, your EAI value is going to be 1 because your evaporation area is equal to that of your projected ground area. Whereas for this three-dimensional material, you're starting to get EAI values that are greater than 1 because you can take advantage of this side area for evaporation. And so when we compare how increasing our EAI value affects this production rate of water, what we can see is that increasing EAI does result in this kind of increase in evaporation. And this makes sense. We are having more area for evaporation, thus our rate of evaporation normalized to kind of our spatial requirement is increasing. And so to kind of give you a size comparison, previously we're at 5.9 square meters, and as we increase our EAI value, we're decreasing to we're at 0.55 square meters. And so this is getting closer, but still significantly, it's still roughly almost 4 times the size of RO. So we're still kind of pushing to see how can we improve this further. One advantage of our three-dimensional materials is that because they have kind of this third dimension, they're able to absorb light kind of on the sides of those materials. And how we've been testing these in the lab has been—
Shut the fuck up!
how we've been so yeah, how we've been testing these materials has been with this kind of lamp fixed at kind of like above solar noon conditions for like multiple hours a day, which is far from what we see in reality. And so a model that I'm going to show you here is basically the light intensity striking the surface of this three-dimensional material throughout a given day. And this solar sun icon is kind of meant to show where the sun is at any given point. And so what you should see is kind of in the early parts of the day, we're getting light striking the sides of our material. Whereas as we get closer to solar noon, which is at hour 12, the top is actually what's getting the majority of the light. And then in the later part of the day, we kind of get light hitting the other surface. And so this is great because not only are we having additional area for evaporation, but that area is actually getting exposed directly to sunlight as the sun moves across the sky. Looking at this experimentally, we're looking at kind of the effect of this solar angle. So at 0 degrees, it's kind of like at solar noon. And then as you increase, it's like closer to sunrise or sunset. And what we saw was that as we increase this angle, we're actually seeing higher rates of evaporation. And this is actually the opposite trend that you would see for a two-dimensional material that actually sees kind of this decrease in the evaporative flux as you increase the solar angle. And then one final thing I wanted to point out to you guys is what happens when you introduce airflow across the surface of our material. For both the flat and the cone, or sorry, not the cone, the cylinder, we do see an increase in the evaporative flux as we increase wind speed across the surface. But the response with our three-dimensional material is much more significant than the two-dimensional one. And basically what's happening here is that as you blow air across this surface, you're actually creating kind of an area where you have low humidity where evaporation is taking place, which is what you want. And then that would enable us to create high humidity somewhere else, say we were trying to condense that water. And then kind of going back to this idea of kind of the spatial footprint or how big this is, when you introduce this, airflow, we're actually kind of within, the same order of magnitude as this RO system, slightly bigger, but less than double the size that is required for that to hit 75 gallons per day. And so those are kind of like all the different ways in which we were trying to increase this evaporative flux. And there's our little guy, and I'll pause for questions. I see Mrs. Hartford's joined, so.
Yes. Do you have a question, Mrs. Hartford? Your hand is raised. Oh, I have to unmute you. Okay, there we go.
Okay, so my question, and maybe you're getting to it, is what's collecting the water that's evaporating from this contraption?
Yeah, that is a beautiful segue into what I'll talk about next. Yes, you're right. We've focused 100% on just evaporating this water, which isn't useful in slaking anyone's thirst. And so that's what we're moving to in kind of this next phase. But yeah, I like where your head's at.
Okay.
All right, excellent question. Now we've got a question from Taro Sakai. And he's saying, obviously the power source is solar light, but what if one day it's cloudy or rainy? Do you just move on and wait for the sun to come back?
Yeah, no, so what's nice about kind of this airflow is that it's starting to, because we're using this, alternative energy source. And so it depends on, how you power this fan. But if you have this airflow, you are less dependent on the sunlight, promoting this evaporation process. You basically are using kind of the low humidity conditions to kind of prompt evaporation to take place. But you're right. I think that what we've shown here is a lot of this has been done in the lab where, we're not simulating clouds or anything like that. And I think that is a big concern for a lot of these solar based technologies, is that you do have to kind of account for weather. But with kind of the addition of this fan, that is helpful in terms of increasing the rate without its dependency being solely on solar energy. That's a really good question, though.
Okay. Not seeing any additional questions at this time. I think we have one more. Is that right, Dr. Finnerty? We have one more question opportunity.
I think so. I think this will take us to the end. So
yeah. So we'll take it to the end, and then we'll have a chance for people to ask questions when we get there.
Great.
Perfect.
All right. So as Mrs. Hartford astutely kind of pointed out, I was like, what about condensing the water? And basically, the conventional way of condensing this water is using this kind of solar still design that you see here. Basically, how this works is you have kind of your setup over here. It'll evaporate water, and then that water will condense on this upper surface. When you get enough condensation, you get these droplets to form. And when they get large enough, gravity will take over and they'll slide those droplets down to your condensation side of your still, and then you're able to produce that water. Now, the problem with doing all this in one stage is that when you evaporate the water and condense it kind of in the same unit, you're creating really high humidity conditions. And like we were just talking about, the lower your humidity, the higher your evaporation rate. So basically all that work that, if we were to use a system like this, all that work for increasing this evaporation rate is basically goes out the window because it's being suppressed by this really high humid environment. And so what we propose is developing kind of this alternative condensation apparatus. And basically how this works is it has two different stages. So you have this evaporation stage and then this condensation stage. And the evaporation stage, it has our material kind of in the top where it can be exposed to sunlight. We introduce these fans to kind of induce this airflow. And what that does is it takes this warm, saturated water vapor and it transports it from the evaporation stage down to this condensation stage. In this condensation stage, you'll notice that the device is actually submerged in cool water. And so what we're envisioning for this system is that it'd be kind of a floating desalination device. And it has these condensation pipes, so that's what these circles are. And in those pipes, the cool water is able to kind of flood in and fill in those spaces, whereas the outside, you basically are just seeing these copper pipes cooled down by the internal fluid. And so what this does is it creates a really low temperature environment for condensation to take place. And so this warm saturated water vapor, as it comes down here, it will start cooling off. As it cools down, the air can't hold on to as much water, and so it has to release some energy, and it does this by condensing water onto the pipes of this system. And then the air will kind of eventually get pushed back through to the top where it can cycle back again. And this is the apparatus we built, and it's easy to say like, oh, here was our idea, and it was this simple to make it. It was not. And so what I wanted to do was kind of walk you through the process that we went through in designing this prototype. And hopefully it'll be useful for any of you guys that are trying to build, anything, whether it's science related or not. These steps will hopefully help, save you some time and maybe some money. But I think, one key step for us was in building this desalination device was first kind of taking inventory of like what materials we're using and what our fabrication capabilities are. We primarily use this acrylic plastic. It's just this clear plastic. You can see it has a blue covering here. And one thing that's kind of like that I had to get used to is it's easy to kind of sketch something on your notepad, but once you have the material, these materials have like finite thicknesses. And so, drawing a connector here seems simple on paper, but you have to kind of file down both sides so that they can fit flush to one another. So when you seal it, it creates a nice seal. And that was something it was helpful, like organizing what materials I was going to be using ahead of time when trying to realize the design. The other thing is once you know what materials you're using, knowing what you can do with those materials. So from this device, you can see that this panel here, we need kind of like all these very precise circles, and they have to match, those same circles on the other side so that we can send a tube through it. And in order to do that, we used a laser cutter, which is kind of what it sounds. You basically put your plastic into, it almost looks like a photocopier, but you put it in there and you program it to make very specific cuts, and it does it actually fairly quickly using kind of a laser. And then another thing I had mentioned before, we needed to file down the sides of certain pieces of plastic so that they fit nicely together. And using this saw table, which basically has this circular saw up, kind of coming out of the table that you can kind of push your materials across, we could actually angle that saw so that we could get very specific kind of angles of cutting onto our materials. So yeah, just taking inventory of the materials and your fabrication capabilities. And then once you have kind of an idea of that, you can organize your design. I was using AutoCAD to do this. So that's is like computer aided design. I might have the acronym wrong, but you basically can design your system in this kind of digital space. And in doing that, it's really useful in helping you understand like how these pieces are going to fit together, and keeping in mind like how you're going to assemble it eventually. So that's how we kind of organized our design. And then we went ahead and machined our materials. Another piece is, if this is your first time doing it, which this was my first time doing this, you want to make friends with the people that are working in the machine shop, because they have a lot of expertise and they can make your life so much easier. And so I got a lot of help on like how to use the laser cutter, how to cut these pieces, and like different practices that they recommended. So yeah, become friends with your machine shop people if you can. So they helped me cut these materials out. Then it was assembling the materials. What's nice about acrylic is you can make these really nice connections. You basically will put kind of the two surfaces of your acrylic together, and then you'll kind of inject this solvent in. And what that does is it dissolves kind of the two plastics into one another. And then when that solvent vaporizes, you'll basically have one piece of plastic. And so that's what we were using all along here. And then the final step, once you have it, what you think is working, you go and test it, make sure there aren't any leaks, seal up those leaks if they exist. And that's kind of this process that we took for this. Now, what I've walked you through is kind of brought us close to when I was told to, not come back to lab and the shelter in place was put in effect. But we did start doing some preliminary testing with our modified condensation device. And one thing we wanted to look at was the effect of these different lids. So this closed lid is kind of like what we were describing before, where the airflow is just purely on the inside of our device and it's just circulating. The open lid is similar, so there's nothing stopping the air from circulating, but it has this big window here that allows for air to kind of freely come in and out of the system. And then finally, we had a fancier lid, this once-through lid, that created this barrier, and it also had that window, so that airflow that was going in could only go through the system once, and then it was forced back out of the system. And we were curious what the effects of these different lids would have on our not only evaporation, but our condensation rate and efficiency. And so you can kind of see the comparison of these lids here. The open lid by far was the most evaporating lid, but when it comes down to condensation, which is what we actually care about, it didn't show that much of a benefit over, say, the closed lid. The closed lid actually performed worse than what we were expecting. And I think this has to do with the rate of airflow. And so what was happening was that our airflow was too high. And so it was basically mixing all the air together. So we weren't getting these discrete, like warm evaporation stage and cool condensation stage. It was just kind of like a lukewarm singular system. And so that was kind of something we learned there. And then this once through lid, we were seeing some marginal increases in the condensation compared to the other two. But you'll notice that we have these temperatures above all of them. This was the high temperature for each of the days. And so that was one parameter that we weren't able to control since these were tests that were done outside. But we were able to repeat this closed test under two different conditions. One where the high for that day was 23 degrees Celsius, and one when it was 33. So it was a really hot day. And what we saw was that when we have this increase in our external temperature, that did a lot for us in terms of making these kind of stages more distinct, and really improved our condensation and production rate as well as our efficiency relative to evaporation.
I'm going to jump in there if you can go back one slide, Casey. So for those of you who don't know Celsius, 23 degrees C is about 72 Fahrenheit, whereas 33 degrees Celsius, that's 90. And
Yes.
this is Berkeley and it's 90. That is really hot.
Yeah. Yeah. That kind of ties in with like, this was in and around like one of those PG&E outages. I don't know if you guys heard about those, but in Northern California, PG&E just like shut off power to campus, and they didn't give us much of a heads up. And this was around that time because it was really hot during that time, so they were worried about fire risks. So and so that kind of brings us to the close. What I'm going to be continuing to work, I'm hoping to graduate in the next year or so, and then I'll rightfully earn that title of doctor. But there's always lots to do in terms of characterizing these three-dimensional materials. Something that I want to look into is kind of the continuing to investigate the effects of salinity, like working with like realistic seawater and seeing if the performance is similar to kind of our sodium chloride. We've been representing seawater as sodium chloride, which is not actually the case. And so seeing, are there fouling effects? Are there long-term effects of, not using kind of these very simplified solutions? And so that's something we're looking into. This will play into kind of improved designs for this condensation skid. And there's a lot of things to test in there. As I mentioned before, the lid type, the airflow speed, how closely we pack the sticks together. And that's, only on the evaporation side. There's, an equally large, if not larger world on the condensation side that will probably be outside of the scope of my PhD. And then, going back to this idea of, we're working with someone who lives in Indonesia, who's going to be conducting these stakeholder interviews. So that would be with potential users, with government leaders, different community organizations, kind of understanding this ecosystem and, who would potentially win or lose if we were to try to implement a solution, and how can we do that so we can maximize the amount of winners in terms of implementing this technology. And then we're hoping that would lead into field testing. And, I put these arrows to kind of, mock the idea that this is a very linear, progression. As, you guys know, with research, it's all iterative. Improvements in design are going to lead you to want to characterize more things, which is going to inform what questions you ask these stakeholders. And then, those relationships will affect field testing. But it definitely is kind of this jumble that you're trying to move all these pieces forward all at once with, success here and there, but a lot of failures along the way. So with that, I wanted to kind of open it up for questions. That's, the end of the presentation, and want to thank, the Laguna Beach High School staff for inviting me here to do this presentation. It's always great to kind of check back and touch base with you guys. So yeah, thank you guys.
Okay, we're going to check the chat and see what questions we can ask to Dr. Finnerty. So the first question is from Mr. Myers. Does the ISVG material degrade over time, or is it infinitely reusable?
So it will degrade over time. We haven't tested it long enough to fully vet that, but yeah, just my suspicion is that there will be a degradation over time. I think one thing that we've seen with it is kind of when it's exposed, like the sun's really powerful. And so when you expose anything to enough sunlight, chemicals will start to break down. And so I think the closest thing I've seen to kind of this degradation is like we ran, multiple tests with the same material that the color starts to lighten a little bit. So that's kind of one failure mechanism that we may be observing.
Okay, next question is from Taro Sakai again. And
Awesome.
He's wondering, how long does it take to make one of these desalination devices?
Yeah, so I would say if they were the only thing I was working on, it would probably have taken maybe 2 to 3 days. A day or so to get the design and then like turn it into drawings, send those drawings to the machine shop guys. they have their own schedule, so it kind of depends on like how quickly they can turn around. But they've been awesome and have really been able to turn things around really quickly. And then assembly is actually fairly quick. They recommend letting it sit overnight so that the solvent has time to fully evaporate. But after that, you're pretty much ready to go on day 3.
Okay, our next question is from Amar Patia, wondering, is there potential for this to be a profitable venture?
Yeah, so that's that's always a question we ask. I think that water has traditionally been a very not profitable business. It's everyone needs it, and yet no one wants to pay for it, and so that's why water is fairly cheap. And so because of that, a lot of these water utilities are struggling to make ends meet because the water that they're selling can't be sold at the price that it might be worth. But at the same time, if it were sold at that price, that would exclude people from accessing it. So it's this, there's all these stakeholders that are kind of pulling things out which way and another. I personally think that if you're going to make a water treatment technology, you shouldn't rely on selling the water or selling the device to purely just to treat the water. And this kind of ties in with a question that was asked earlier, is that where would your revenue stream come from? I do think that there may be potential to use that salt. So taking that salt, and rather than it just kind of going into a landfill or going back into the ocean, taking it, processing it, and selling it, and using that to kind of fund the whole operation.
Excellent. I think this will be our last question. It's from Luca Alganian, wondering, would the material need to be cleaned over time or replaced? And if you did go through a cleaning process, do you have any idea how difficult that would be?
Yeah, so a slide or an image I didn't show you guys in this is kind of what happens when scale forms on the 3-dimensional materials. And so similar to the 2-dimensional ones, the formation of that scale doesn't decrease the rate of evaporation. But what's neat about it is because it's this 3-dimensional figure, I'll use my pen here, you kind of get this like formation of this scale at the top, and it'll actually reach like kind of this critical size where kind of any additional scale that forms gets like too heavy and it'll actually fall off. And so what's kind of nice about that is that kind of in contrast to the 2-dimensional material where it's just building up on top of the material, this one actually will kind of reach this maximum size and the rest will fall off. And one idea that we had was like having kind of this like slanted base so that when scale falls off, it would kind of like gravity kind of take it away into a side collection bin that we could take off. And so we're one thing I learned from my time at work is that like things are always going to foul, whether that's scale or bacteria or something like that. And so what's nice about this process is we're not trying to fight fouling from taking place. We're just trying to like prevent it from causing structural instability or like causing our system to weigh too much and affect that. And so if we can kind of create this passive way of collecting the salt, then we can take that out and that really extend the maintenance time that would be required for the system.
Yeah, so you're saying it's essentially going to be self-cleaning, and you could get the salt and sell that, and it's a win-win-win situation. Huh?
Oh yeah, it's on paper it all works out.
Okay, that is going to be the end of our presentation today. So Thank you all for coming, and we hope to see you again at a future webinar. So take care for now. Teachers, I will ask you to stay on for a minute, but students, this is your time to say goodbye, and thank you for being here.